you all did the very first homework. Quite impressed by the many levels of analogy that you took up and also the explanations that you gave for both the concepts that you have introduced as well as in terms of the reasoning for the analogy. Before we venture into the next aspects of the math behind what we are doing, I'd just like to explain a few things on the board. A little bit of it will be a recap of what we have done so far, but most of it will be to bring in the newer concepts. Okay, so essentially we are looking at dynamics, and we are looking at it from 4 different perspectives over here. One is in terms of the dimensionality involved, where we are looking at problems to start with very simple, which will have only one independent variable, what we will call as the 1D problems. Then planar problems, where you're just looking at one plane and introducing a particular rotation if we are dealing with rigid body dynamics. So that's essentially your 2D. And the reality, which is predominant, which is a 3D kind of a model. It's very interesting that your syllabus at Georgia Tech for the dynamics course AE2220 includes 3D, because as far as I know, most schools in the US at least, including MIT, Stanford, etc., at the undergraduate level when they teach a dynamics course, they do not have any 3D modeling at all. So they stop with the planar kind of a modeling. So I'm actually quite happy that they're bringing in that, because that's where, for example, in aerospace engineering, we know that we cannot deal with a roll and yaw for that matter, which are very, very important things, unless and until you get into 3D. You will be limited to dealing with just pitch, forward and the vertical motion for most parts with your planar kind of analogy that you have. So this is very important that we are going to cover all these aspects, and we will spend some time on the planar problems, but very soon we'll get into the 3D aspects. So it's important for us to understand this gradation. And like always, we are trying to complicate problems, get to the more complex ones from the most basic or things that you understand. And every now and then I've been bringing in some examples from your high school physics as well, and high school math, the calculus in particular, which is going to make you feel comfortable in terms of the transition that is taking place towards the more realistic kind of problems. In 1D, we already saw, but I probably didn't explain it in this particular manner, that we are going to start within 1D. It could be one dimensional on a straight path, or it could be on a curved path. And based on that, you have what is known as rectilinear, and curvilinear. And similar to that, in 2D, you would have planar and surfacial. Okay, and on the other hand, in 3D, which is what is kind of interesting, you would have what is known as Euclidean geometry. Named after somebody whom we briefly mentioned during our discussion on the history of dynamics, and non-Euclidean geometry. Okay, Euclidean geometry is what you are familiar with from your high school geometry or even probably middle school, where it may not have been taught in this particular way, but essentially you make certain assumptions in terms of how you're going to get to the theorems, because theorems will need a starting point, and for that starting point you have what are known as axioms or propositions. So typically axioms and propositions are not stated because they seem to large extent intuitive and therefore completely ignored, but I would urge, if you have forgotten some of that from this school geometry, to kind of look through some of those propositions, because that will help you know when that particular geometry or the theorems based on those geometric aspects are actually valid and when they are invalid. Okay, so when those propositions fail, obviously that Euclidean geometry fails and you have to go into the more generic non-Euclidean kind of a geometry. A very simple example would be if the way we thought the earth was as a flat land ending somewhere at some point, and then we recognize that it is actually of a certain oval kind of a shape, an ovoid kind of a shape. And then now you're essentially talking about if you're looking at vehicles moving on the Earth's surface, be it on water or land or on rail tracks, you're essentially looking at a surface motion, and that's a curved surface. Okay, so what you typically can look at, for example, in that kind of a geometry is maybe you can even take a step back, and every one of these are essentially like Euclidean, non-Euclidean, Euclidean and non-Euclidean, right? So whenever you're looking at, say, like rectilinear or planar or some kind of a cuboid kind of a geometry where you're essentially having everything along straight lines, and you can break up any arbitrary motion into those three directions which are mutually orthogonal to each other, then you end up with the Euclidean kind of a geometry. If you're not able to do that, there is some kind of a curvature involved, then you're essentially talking about non-Euclidean. It's very easy to see in 1D that it is curvilinear and in 2D that it is surfacial, but essentially when you're looking at 3D, it's a little more complex to understand non-Euclidean geometry over there. Now, irrespective of which kind of a model you're going to look at it over here, the dimensionality will refer to the number of independent variables that you can do the problem with. Sometimes you might introduce more independent variables than necessary, but you may not need it in the sense that you can do without it as well, but introducing them might simplify some of the processes. So then you introduce it and then you do away with it towards the end of the derivation process. We'll see examples of that too. Now that's as far as these three models are concerned. Yeah, go ahead.
Good question. So if you're analyzing, let's just say, the motion of a plane across the globe and it's going in a straight line, like relative to like a latitude line or something,
Mm-hmm.
if it's going in a straight line, then would that be Euclidean? Like, would we analyze it as Euclidean or non-Euclidean?
Excellent question. And I'm also glad you brought out the concept of latitude. So latitude and longitude would essentially become like your x and y, but in an angular sense on a spherical surface or any curved surface like that, right? So now if you're looking at things like that, then essentially a lot of people will continue modeling it with Euclidean geometry, but it is subject to a little bit of error. Maybe from an engineering perspective, you are able to live with it, because it's all the question of what is the curvature that is involved, or radius of curvature, compared to the distance that you're essentially considering in your dynamic problem. Okay, so let's say if you're looking at a long haul flight, which or an intercontinental ballistic missile, it's traveling a fairly large distance compared to the radius of the Earth even, right? So which means that you will have to take into account some of the non-Euclidean aspects, without which you will incur errors which you may not be happy enough with in terms of the end results. But if you're looking at smaller distances, like suppose you're just traveling across Bangalore, it's let's say urban air mobility you're talking about, you're going from one terrace to another terrace at the other corner of the city, then the distance is not large enough compared to the radius of the Earth. So the curvatures that you're dealing with are much smaller, or radius of curvature is much larger, which essentially means that even using Euclidean kind of a geometry will still not give you larger errors. So it might be accurate enough.
I guess what my question is more like, it makes sense intuitively that, I don't know, if you're going, like if you're flying 100-mile distance, you don't necessarily need to correct for that angular motion, like around the center of the Earth. But if it's like, I don't know, Atlanta to China, then obviously you would have to.
Right.
What I guess what I'm asking is, couldn't you theoretically, if it's going in a straight line, like you're assuming it's a straight line from Atlanta to China, for example, like Beijing, then couldn't you just take like that cross section of the Earth and then calculate the arc length distance, and then that would be Euclidean, right? That would be a Euclidean calculation.
Good point. There, essentially, when you're doing a long haul flight, like as you mentioned, example of Atlanta to Beijing, you typically, ideally, speaking, would want to fly on what is known as the Great Circle. Okay, so the Great Circle is essentially something that you arrive at from using the calculus of variations, which is, as I said, dealing with functions of functions or functionals. So you will be trying to minimize that particular distance on a curved surface. Okay, so giving the curved surface as the constraint on which this transition should take place, you will calculate the shortest distance, and that will never be a straight line. It will be a curved path, and that curved path would be a great circle. Okay, but in reality, what happens is that might be flying through, let's say, Iran or one of the more dangerous regions today, like let's say Ukraine, or it might be flying through Palestine, Hamas, etc. So then you will have to make transitions. Okay, so there are practical concerns as well over there. So when you're making those changes, the flight path changes, or the flight path planning becomes a very, very critical thing. I don't know if you have already been to the flight path planning lab. Maybe it's this week, I think. So probably tomorrow or the day after you'll be looking at that. Okay. So there you'll actually be taking into consideration some of these non-engineering constraints, some geopolitical constraints and things like that. Okay. Because that's the practicality of how we live today. We need to bring those things into account. And whether you're doing that or not, essentially, once you're on a curved surface, some of the propositions of Euclidean geometry will fail. See, there are totally 4 propositions that everybody talks about, and there is a 5th proposition which some mathematicians consider a proposition, some think of it as an axiom or a theorem, which is a fallout, right? So depending on that, the very classification, what is Euclidean or non-Euclidean, is not like a very, very rigid line between that. Okay, so let's not worry about the name or nomenclature involved. It's a question of going into the actual math and the physics and the assumptions that is made. So the assumption that is made is coming from those propositions, more often than not valid. So when it is not valid, you have to go for something that is more generic.
Okay, I understand, but I'm asking, can you turn a non-Euclidean situation, if it's simplified, can you calculate it as if it is Euclidean?
Yeah. So that's what is called as a conformal mapping. So when you're having some more complex situation, you can map it onto something that is something that you're familiar with, or something that is tractable in a more simplistic modeling approach, analytical or numerical. Okay, so that's always possible. Yeah. So depending upon the specifics of the problem, how accurate that conformal mapping is will differ. And there's also a possibility of you writing the expression for the function, which is the difference between the two, and minimizing that. So that becomes a part of exactly. Right. So you can minimize the error to the level that you are comfortable with. Anybody else? Any questions on this? Okay. So this is as far as the dimensionality wise trying to divide this problem is concerned. But irrespective of how you go about this particular division, and we'll look at 4 more divisions. So one is based on the motion, and irrespective of how you're going to, which I think we already anyway discussed, so I'll very briefly mention that. That's your kinematics and the kinetics. So in one case, you're looking at the description of the motion. The other case, you're looking at the causation of the motion. Okay, what causes the motion, right? So that is as far as those two are concerned. Then you're looking at in terms of the kind of objects that you're dealing with, which we already saw were the simplest case being the particle, which is what we will continue to work on for maybe early part of this week before we take up the rigid bodies also in this course. First the planar motion and then the 3D motion. And then of course something that we are not going to consider as part of this particular course is the flexible bodies. So when you're essentially bringing in the structural dynamics. So dynamics of rigid bodies is just called dynamics by itself. But when you want to bring in flexible bodies, you typically call it a structural dynamics, because the structural aspect will bring in the stiffness, which is a finite stiffness instead of an infinite stiffness that you have in this case. So rigid essentially means that you're assuming the stiffness is so large that you can treat it as infinity. But irrespective of how you're going to deal with this, or in terms of the simplicity or the complexity of the problem, you always have a set of 3 tools that you have to start off with, either implicitly or explicitly. And those 3, again, we've been talking about it, but not in a formal sense like this. So I'd like to mention those 3 tools. The first thing is, of course, the frame of reference, at least one of them. But in general, you could have frames of reference, which essentially means that you're trying to describe whatever motion, not in an absolute sense, but in a relative sense, right? So it's impossible to express it in an absolute sense, because then you should not have any frame of reference. Essentially, there's no observer, and you're essentially talking about an inherent motion in the particular object, which falls into the realm of metaphysics more than the physics. Okay, so whenever you're talking about motion, you're essentially talking about relative to something else, and that something else could be an actual body itself, another rigid body, for example, or it could be something that you are imagining up. It's a figurative kind of reference frame. It could be fixed to another rigid body or not. So that is the important thing about that. And as we have been discussing, all the laws of motion, the way Newton states it, are all valid only for inertial frames of reference, and there's no such thing as an inertial frame of reference. So it's a question of what best you can get to, depending upon the accuracy that you desire. Okay, so in this we would have, for example, let's say an aircraft fixed frame of reference, which we will call as A for aircraft. We could have an earth fixed frame of reference, which, because our planet's name starts with E, we will call it E. And we will always use this kind of a circle around the letter, usually uppercase, in order to denote one of these frames of reference. Okay, then you could have a heliocentric or what we call as a sun fixed frame of reference. Okay, and eventually you could also have what is known as a zodiac fixed frame of reference, which is essentially your constellations that you're familiar with. Also from a point of view of astrology, you know that these are mentioned as the 12 different classes that you have, etc. But that is essentially taking it to a different direction. But that astrology is based on astronomy, and astronomy is essentially the observation of the constellations that has been made. And with respect to those constellations, you have the zodiac signs, and those are a little more reliable. So in terms of reliability, this increases as you go in this particular direction. Okay, so in terms it will become more complex, because when you're trying to do it with respect to the zodiac, you have to take into account the motion of our solar system and the galactic systems, including the sun, and then within that you have to look at the motion of the earth, and then you have to look at the motion of the aircraft in that, and then some body which is on the aircraft, let us say a body B, which is could be a flap, it could be a rudder, whatever it is, some particular body that you're talking about, which could be moving with respect to A. Okay, and many a times, even though you might be treating Z as the frame of reference, you will introduce these intermediate frames of reference in order to go in a step-by-step manner and eventually look at the motion of B with respect to Z. Okay, so more often than not, at the most you will stop with, especially in this particular course, we will stop with an earth fixed frame of reference. We will not go beyond that to a sun fixed or a, it's not that it's difficult, but it's just that it essentially messes up the problem a little more, just to make it a little more accurate, which compared to the speeds that are involved, the distances that are involved, etc., may or may not actually be worth the effort. Okay, so that's the reason why we typically might talk just about B, A, and E. Okay, so that's the very first step, irrespective of what problem you're solving, and I would like you to do this when you present your solutions from the next homework onwards, which are all based on dynamic problems, numerical solutions, etc. Always start with at least one frame of reference. Some problems might require more than one. Usually you will have two, because it's one body with respect to another body, or one body with respect to an imagined frame of reference. So you will have at least two frames of reference. Then coming to the second thing, for that particular frame of reference or frames of reference, you will introduce what are known as the coordinate systems. So this is again very, very important. So once again, for example, if it is the B system, then you essentially introduce a frame like this, which is attached to that particular body B, so that on that you are having the coordinates, let's say X, Y, and Z. Okay, now because we might be doing the same thing with the others as well, we have to distinguish this in a particular way. For example, we could use subscripts to distinguish that these are all this is the coordinate system associated with B, so I could call it XB, YB, ZB, right? So that's something that is what is an example of the coordinate system that you introduce. Similarly, you would have an aircraft fixed frame of reference where you will introduce your XA, YA, and ZA, right? So now this this could be the body which is moving with respect to the aircraft, and then you go on eventually at least to the Earth in order to understand the treating Earth as a reasonably good inertial frame of reference, and therefore applying the laws of motion the way we know it, right? So for each frame of reference that you introduce, you will introduce a coordinate system. And we also said in the previous class that these need not be straight lines like how I have drawn over here. They could be curvilinear as well. Okay, so in other words, XB, YB, and ZB could be curves, and they need not be mutually orthogonal to each other like how I have drawn it. But for most practical purposes, this should be good enough, and this is what will lead you to the simplest kind of a mathematical model. But many situations might demand going beyond that. And some examples of that would be what we already introduced, the Cartesian, which is the simplest. Then we could have a polar in 2D, which is in the 3D would be cylindrical. So whereas the Cartesian will be in terms of, let's say, X, Y, Z, this would be in terms of just an R theta, and this would be cylindrical, would be the 3D version of that, R theta Z. Okay, the Cartesian 2D, of course, we could drop off Z and have only X and Y on the plane in which the motion is essentially you're talking about, right? You could also have the spherical, in which you have an R, theta, and phi, which is similar to what Lalita was pointing about latitudes and longitudes, in which case a two-dimensional motion, you will not talk about R, assuming it's the Earth is, even though it's obloid, you can treat it as a sphere of a constant radius, and then you keep R constant and you only deal with the phi and the theta, the latitude and the longitude. But the R itself can also be depend on the terrain, especially for land-based vehicles. It could be the altitude you're talking about. So essentially you're talking about from the sea level, mean sea level, what is the altitude. It could also be for certain problems you're going all the way up to the center of the Earth, and you're talking about the mean radius plus the altitude above the mean sea level, which is the total R that you're talking about in that particular case, right? But in many problems involving that, you'll only be considering phi and theta, the latitude and the longitude. Now, These are things probably you're familiar with again from earlier courses on math, etc. You would have in particular worked on a lot of polar coordinates, cylindrical coordinates. You would have been briefly exposed to spherical coordinates, but probably not done too many problems compared to cylindrical coordinates, etc. Right? One thing which is very, very useful in dynamics is a fourth kind of a thing, which we call as the natural coordinates, which is natural to the motion. So what we mean by that is that you have a certain path, and it's especially useful when you're looking at lower dimensions like curvilinear or surfacial, which are 1D or 2D. So taking the simplest example of a curvilinear path. So you have like what we demonstrated in the previous class, let's say a particular curvilinear path like this, and you're introducing let's say a coordinate along that, which you call as S, and only one of them is sufficient for this. That S, of course, will be a function of time. So this is essentially your arc length. So how much you have traversed on that particular thing, and this will all will have a particular datum somewhere. You're starting at S at 0. We could probably define that as another variable, let's say S naught, okay, or you can treat it as 0 even, okay, without loss of generality, and then you could say what is essentially happening beyond that particular point, right? So we have a particular instant of time when we know probably the information, which we will call as the initial conditions, and then at some arbitrary time t, we should be able to know what is this S of t, what's its derivative, first derivative with respect to t, and the second derivative with respect to t, which will be related to the so-called velocity and the acceleration. But remember that all of these are expressed in the form of scalars right now, because it's just on a path, and so more appropriate to call this instead of velocity would be speed. Right. So, and similarly, your acceleration would be the magnitude of acceleration along that particular path that you're talking about. Otherwise, you would have to express the particular direction, and that direction is changing along the path. Now, at that particular location, if you draw a tangent and take a unit tangent, which means the magnitude of that vector is 1, then you call that as ET. Okay. Sometimes you might write this with a cap, ET cap, hat, instead of an underline. But I'm writing all vectors with an underline, so I'm just putting the underline over there. Okay. So this is a tangent, and how you determine that tangent is, for which also you need to go to the first thing, which is introduce the frame of reference and the coordinate system, even for the simplest case of a 1D curvilinear kind of motion that you're talking about. So in other words, I can introduce somewhere over here a particular frame of reference, let's say an earth fixed frame of reference, and then I will introduce the coordinates xe, ye, and ze, and then this origin O, from which to that particular point I can draw a straight line, and that becomes a vector. So let's call this particle P, which is traversing on this particular path. So that vector is your ROP, starting from O and ending at P. It's essentially what we call as a position vector. One, because it is a vector, and the other is because it determines the position of a particular point P. Therefore, we're calling it a position vector. And this is one of the important starting points for all dynamic problems, to identify the position vector once you have all the other basic parts set up on that. Right? I haven't yet talked about the third one here. I'll come back to that. Now, if you want to determine that ET, you have to all that you have to do is to take a derivative of your position vector with respect to that arc length. So your ET is defined as So all of these things that I've written in this notation are very, very critical. One is, what is the vector whose derivative you're taking? That is the position vector of P with respect to what? The point O, which is the origin of the frame fixed to the earth. It need not be at the center of the earth, it could be somewhere on the surface of the earth also, doesn't matter. Just that it rotates along with the earth on its own axis, and it revolves around the sun along with the earth. So those motions have to be performed by E with respect to S, the sun fixed frame of reference. So that's the vector. What is the derivative taken with respect to? It's taken with respect to the arc length. Now the position vector's magnitude has the unit which is meters, okay, which is essentially the magnitude of this line O to P. That distance is essentially what it is. And S is also measured in the same unit, the dimensionality is length. So you can see that this is a non-dimensional quantity because both the numerator and the denominator have the dimension of length, and therefore it's a non-dimensional quantity, and its magnitude will always be unity, which is why it's a unit vector, and that unit vector we are calling as the tangential vector. So remember, I'm talking of all of this in the context of this 1, 2, 3, 4th system that is usually very useful in dynamics, which is the natural coordinate system. The first vector in that is the tangential vector, tangential unit vector, right? Then you come up with what is called as the normal to this particular vector. In other words, you're trying to introduce two more unit vectors, both of which are normal to this. One of them is called the normal, the other is called the binormal. Okay, so let's go to the normal first. So the normal vector is defined as E subscript n for normal, and that is defined as the derivative once again. And I forgot to mention that the other important part of this notation is the derivative is taken with respect to the earth fixed frame of reference. Okay, it would be different if it's taken with respect to A or S or Z, any of those other frames of reference that we introduced. And of course, with respect to the particle itself, if we had taken the derivative, it would have been 0. Okay, because if it's with respect to B, because this is fixed to B, and essentially it would be 0, right? So this normal, on the other hand, is En, which is defined as the derivative of your Et, because now that you have got Et, you can take its derivative with respect to S, and divide it by the magnitude of that. And once again, of course, these are with respect to the earth fixed frame of reference. Okay. Then you can also take what is known as the binormal. Instead of calculating it as a derivative, now that we have two of them, we can take the third one as just mutually orthogonal to each other, and therefore the binormal, which is represented by E subscript B, will just be given by Et crossed with En. Okay, so that's the set of three unit vectors that you have associated with natural coordinate system, right? Similarly, you would have in the spherical coordinate system ER, E phi, E theta, which are all unit vectors. Magnitude is, I'll come to you, Lalita, which will all have a magnitude of 1, and which will have different directions. In this case also, they are all mutually perpendicular to each other. Similarly, if you're looking at the polar coordinate, you'll have just two unit vectors, ER and E theta, perpendicular to each other. Cylindrical, you have ER, E theta and EZ, mutually perpendicular to each other. And in the Cartesian, of course, the simplest case that you're all very familiar with, EX, EY and EZ, which will be along those. In this case, of course, it's the body fixed, but if you draw a similar thing for Earth, you will have the coordinate along with that. So in this case, it would be the EXB, okay, and EYB and EZB. So these are once again unit vectors. So once again, there was a question related to this earlier, and I had answered it already. So you just have to refresh that there's something called the measure number. something called the unit vector, and the product which is called as the component. Okay, so never confuse between these and never interchange whether you're writing something or you're speaking orally. Be very, very precise about these things. The measure number is a scalar, it's just a number. The unit vector always having the magnitude 1, so it has just the direction that is important to be specified, and then the product, which is the component, which is also a vector. Yes, Lalita.
Quick question, what's the triangle on top of the equal sign?
Yeah, so this essentially means definition. So whenever I just put an equal, it's just an assignment. You're assigning something to something else, okay? Whereas as soon as I put a triangle on top, I'm introducing a new concept, a new variable, and that's essentially a definition. Okay. So we'll use it quite whenever we are introducing new concepts. Like for example, in this case, we didn't know what is a binormal, what is a normal, what is a tangential vector. So we're just essentially defining that. Okay, that particular.
And another thing. So let's just say we're analyzing the energy of a curved path, or like, I don't know, like a non-linear path. We're trying to analyze like another aspect of it. What if we try to make that graph linear? Would like we linearize data? Would that technically be like creating a natural coordinate system, or is that just data analysis?
Yeah, so if you're looking at this particular example that you're talking about, so you're looking at the traversing point or particle P is identified by once you fix a particular S, right? So in that sense, there's only one measure S that is necessary over that. You don't even need to deal with vectors, okay? So you can think of this in reality, though it is a curved path, you can conformably map it to what is on a straight line, as long as you're taking the aspects of the math that is involved over there, which could be that same S of t on a straight line. Okay, so this is what we call as not an ordinary mapping but a conformal mapping. So essentially you have to conform that and take all the aspects of that which you're missing out by drawing a straight line instead of a curve. You have to bring in, for example, the aspects of the curvature, etc., as part of the properties of this particular line. Okay, so it is theoretically possible. One of the approaches, in fact, the way we deal with curvilinear systems.
Theoretically, if you have a curvilinear system through 3 different dimensions, like it's curving on the x, y, and z axis.
Yeah.
Then theoretically, could we take like one reference frame, like one view, like if it's a line segment, you can take one view from the top in which it is straight, and then like note the angle and the direction of that, and then one angle from the side where it's straight, and then only in one reference frame it would be curvy. So then you can analyze it in those 2 reference frames as those straight.
Yeah, absolutely.
And
So
that would also be a natural coordinate system?
Yeah. So that's what you're explaining is what we call a subject area called domain decomposition. So we decompose an existing domain into smaller parts, and whereas for the overall domain, certain simplicity or certain assumptions or approximations may not be valid, parts of that domain, certain things will be valid. Okay. So for example, you're talking of a space curve, though I'm drawing all of these on the whiteboard over here on the plane of the whiteboard, and therefore it seems planar. Whatever we have introduced in terms of those unit vectors, these are all valid definitions even in a spatial curve. So even if it's varying, not just having curvature in one plane, but curvature which is beyond that plane. So and essentially you could have curvature in all directions. So essentially that kind of a 3D space curve also you typically analyze by introducing these sets of natural coordinate systems, right? Now the third thing that I just didn't yet name it is what we already introduced. It's a set of unit vectors. Okay, so you have a coordinate system that is only taking the measure numbers x, y, and z. Okay, whereas this is what brings in the corresponding unit vectors which are tangential to that particular system, which is the third essential part of any problem. And this is all of this typically is done right at the start of the problem, even before you venture into the equations, the values that are given, what is unknown, what is to be determined, etc. This sets the basis for all of your mathematical notations and the equations that you're going to write out and eventually solve. Okay, so many a times these are done kind of implicitly, but I would request you, especially at the beginning of your dynamic journey, to look at each one of these explicitly. That way you understand the roles, that important roles, significant roles that each one of these play, because without them, even though you might be dealing with them implicitly, you can actually not really do any dynamic analysis irrespective of the methodology that you choose. Therefore, these play very, very significant roles. Having said that, we will take up an example where we are probably not going to deal with them, because we are going to do what is known as a rectilinear motion, the simplest case, which is just moving along a straight line. Okay, so in which case I don't need to deal with position vectors. I can just deal with the position itself, because I know once I given S, I know where it is. I can deal with, instead of velocities, I can deal with speeds. Instead of acceleration, which is also a vector, I deal only with the magnitude of acceleration, which is a scalar, and all the things that you are aware of in terms of the derivatives of scalar functions, which we summarized, the commutative nature, etc., the various products and how you take the derivatives, etc. All of those will be valid in that particular case, which is what we will take advantage of. Okay, so just like we introduced ET, EN and EB in this particular natural coordinate system, as I already mentioned, in each one of these you'll have a set of 3 unit vectors, and the first one of them will typically be tangential to that particular path that you're essentially taking. So that goes especially for the curvilinear systems that we very briefly talked about in a previous class. If x, y and z are not along straight lines but along curves, then you see that those unit vectors will become functions of, in general, all the 3 spatial coordinates. Depending upon where you are, xb, yb, zb, you will have the definition for these will of course be the same, but the actual expression when you deploy that definition will turn out to be different for each one of them, which is what you have to use. So in other words, there would be functions usually of time explicitly, and sometimes implicitly of s and a few other variables that are involved when you go beyond 1D to 2D and 3D. So this is the summary that I wanted to bring up. If there are any further questions on this, I'd like to answer before we get to the slides. Yeah, I'll just start it and then. Maybe you can switch off these 2 lights. Thanks. Yeah, so now we will start from the simplest, which we said is 1D, and within 1D also it's not curvilinear but rectilinear. So as I mentioned, the prefix here is curvy, essentially talking of a curved path like what we showed here. And this is recti, which is essentially rectangular or straight lines. We are talking about an example like this, right? So that's the rectilinear motion, and for this you don't even need to know vector algebra. So the scalar aspects are good enough. Scalar calculus is also good enough, which is what we will revise over here. So all of the motion is taking place on a straight line, and if you're analyzing only one of the vector measure numbers, which is let's say on the straight line, if it is x, if the x-axis is along that, so your s is nothing but x itself. Okay, and instead of taking the reference over here far away from the path, it's always convenient if you take the, because without loss of generality you can move this reference surface wherever, but you have to stick to it once you have fixed it somewhere throughout the problem, so that you are consistent with it. So instead of having it somewhere over here, I can actually bring it on the path itself. Okay, in this case I bring it to some particular point on the path, and one of those axes will be along that, which let's say the x-axis, and then the y and z will be perpendicular to that. Y and z will not even be used because all of the motion is happening on the x-axis, which in more generic terms, instead of calling it either x or y or z, we can just call it as s of t, which is what we will do over here. On the other hand, remember that we have a general definition for the position vector, which is r, that we introduced in this case from the origin O to the particular point P. Okay, and when we drop off OP, it is understood because we are dealing with just one particular particle and only one particular reference frame, and therefore the O is the origin of that particular reference frame, and P is that only particle that we are dealing with, and therefore we might just call it as R, which is what is done in this particular example. Now you don't even need a vector because you're essentially dealing with distances along that line. Okay, all directions are going to be parallel to this particular path, and therefore there's no need to bring in the complexity of the vector. But remember that all of these quantities that we're dealing with are actually parts of a vector. In fact, it's a measure number along a particular axis of a which is parallel to the path of that particular vector. Okay, so in that sense we can bring in the position vector's measure number. So to just illustrate that, we will take this, let's say and we will have that position vector, which we called as ET, is the unit vector, but it, in this particular case, the way it is identical to your EX. Okay, and it's that particular position vector, that R that we were talking of, from O to all the way to that particular point P, is nothing but x times EX, and its magnitude x is all that we are interested in, and that's what in more generic terms we are calling as S of t. So your position vector R the position vector R is now equal to x times EX. Okay, and that x is what we are defining as S of t, which is this, the arc length along that particular path. And since all the motions are anyway with respect to x direction, so we are just calling R of t, we are defining as the magnitude of that position vector R OP, right? So this is from OP. Did I write that as subscript? Okay. So essentially this is what you have, and which is the R of t that you see on this particular slide. It's a scalar quantity, which is just a measure number of that position vector. So if you understand this overall, then essentially trying to broaden the horizons and trying to understand, extrapolate to more complex problems will become easy, because this is something that you know from your high school math and physics. So that is the R of t. So recognize that this is a scalar measure number, and so we will utilize all the things that are valid for scalars for this particular quantity R of t, right? So if you take the first derivative of that, now no longer do you need to specify a frame of reference, because it's a scalar measure number, though it was a part of a vector. So then you have V of t, all that you have to do is to take the derivative with respect to t. For example, if this is sine t, this would just become cosine of t, right? So then you take one more derivative and you arrive at the acceleration, which is what you see as equations over here. The first equation is defining your velocity magnitude. Again, whenever we say velocity or acceleration, remember that it's a vector, but here we're talking of speed. Though we are using the same symbol v for velocity over here, it's the speed that we're talking about, because we're not drawing it bold or underlined or with an arrow on top. That v of t is just r dot of t, where dot, as we already introduced, is a derivative with respect to time. And it's an ordinary derivative because there's only one independent variable, time, that is associated over here. Even though this is kind of straightforward and silly, I'm trying to explain it in a very precise way, because some of these descriptions will directly be taken over for the more complex problems. So just bear with me if this seems like too childish. Okay. So a of t is the first derivative of the speed with respect to time. So that's your v dot. And now you can substitute for v of t over here, and therefore it becomes r dot of dot, which is r double dot, is the second derivative of the distance that we are talking about, which is the scalar measure number of r, the position vector. But we are talking of that, just that scalar number over there, and therefore once again it's a scalar equation. So depending upon the problem, sometimes we might deal with all of these three variables, that is a, v and r, and deal with just first order differential equations. On the other hand, we can bring in just r and deal the entire problem in r, but we will have to deal with second order differential equations. Okay, so both of these are equally acceptable from a mathematical point of view, from the point of view of the rigor that is involved. Just that the way the problem is tackled is slightly different. The solution methodologies are different. In one case, you have a single variable problem that you have to deal with, r of t, and as post processing, you can always get velocity and acceleration once you have solved the problem for r. So v and a will not explicitly enter the problem. Everywhere the math of the problem in terms of the governing differential equation or the initial value problem that you pose will be in terms of r double dot. The boundary conditions will be in terms of r dot and r, and then you will solve the general governing differential equation. You will get arbitrary constants. You will calculate those constants using the initial conditions, and then you will get all of r. R as a function of time. Once you have that, you can go back. So one part of the problem is solved, then you can always go to these definitions to get back your velocity and acceleration as a function of time. The other approach, as I already mentioned, is to deal with all of these three variables, and then in particular you're looking at r and v in terms of which you have the differential equations, but those will be first order differential equations of a set of equations. A set of equations, the set having of course just two elements, one with respect to r, the other with respect to v, and you will simultaneously solve them in order to get to the solution. Okay, next, if you depending on the kind of problems that we have, even in rectilinear, there are further simplified problems where you're, let's say, just given this s of t, okay, which is nothing but r of t as well, the measure number that we are talking about over here. That's one part of the position vector. So in other words, you're given s of t or equivalently r of t, all that you need to do is a problem might ask you to determine the velocity or the magnitude of velocity rather, and the magnitude of the acceleration. All that you have to do is to recollect your differentiations and then the formula that you have for various functions, and if they're mixed up, then you know how to deal with products, etc. In fact, we revised in a slide in the previous class on that. So therefore, you can directly get the first derivative and then the second derivative. You're done with the problem. Some other problem, you might be given velocity as a function of time and asked about acceleration. Then all that you have to do is to take the derivative of that. In that problem, if you want to get the position, instead of finding the derivative, you have to integrate that in order to get to your r of t, right? So in most dynamic problems, you will find that, I mean, this is a very generic statement, but more often than not, this is true, that differentiation is easier compared to the integration, because integration also involves looking at the conditions and solving for the undetermined constants, etc. So one extra step that is necessary to go in a backward direction to what the differentiation does for you. Okay, now integration is also easy, especially if you have all of these quantities as functions only of time. For example, a particular problem might be posed in such a way that the acceleration is given as a function of time. So once you're given the acceleration as a function of time, then you're asked to find the other two quantities of interest. Again, I may not be specifying each time magnitude of acceleration, but recollect that this we are dealing with just a rectilinear motion, and therefore we are talking only about scalar quantities, which are magnitudes of acceleration, magnitude of velocity, magnitude of the position vector. Okay, so given a of t, finding v of t is just through one integration, and then again one more integration to get out of t. And this, as I said, will involve an additional step because we need to know what happened at a particular instant of time. We will call as the initial conditions, right? On the other hand, instead of starting from acceleration, you might start from the velocity, which might be given in the problem definition, and therefore you're asked to solve for r of t. You have to integrate to get that. You might also be required to get a of t, in which case you will differentiate that. So one of either kind is involved, differentiation and integration. Okay. Now in either of these, because the simplicity that we are talking about, that they are all explicitly functions only of time. But in reality, it can happen that a, v, or r can be function of t explicitly and also the position s, and that case it becomes slightly more complex. Not that it's impossible, but just becomes slightly more complex compared to this simplest case. And we will look at that in the next in the coming slides. Right now, let's focus on this simplest case. Even in this simplest case, there's no one particular approach. There can be four kinds of approaches. In fact, we very briefly talked about these two in the previous slide. But you know that integrals are either of definite kind or an indefinite kind. Definite where you specify the limits of the integration, and indefinite where you do not specify the limits of integration and rope in a constant to be determined later on, right? Now, if you're looking at the definite integral, obviously the two instants of time that are of interest are the one at which we have some information given to us. We will call that as the initial condition or the initial time, and we without loss of generality we can call it 0. But if you are interested in motions prior to that also, maybe you can involve with negative t, or you can call this as t naught in a more generic sense and go from there, right? So this is what we have, and once we do the integration on the other side, remember that all these are coming from the simple two differential equations that define the velocity and the acceleration. With respect to any particular inertial frame of reference, and your acceleration is given with respect to the same frame, you're taking the derivative of the velocity. Okay, so this is a general definition. This is for all cases, this is valid. So this is the generic definition. But in this particular case, in rectilinear motion, we are only looking at the magnitudes, and therefore we are just saying that v is equal to dr by dt or ds by dt equivalently. So that is s dot that we are looking at, and then your a, which is again the magnitude of that acceleration rather than the acceleration itself, you're defining it as the dot of that, right? So as simple as that. Okay, and Further simplifying, in this particular slide, we are looking at all of these just explicitly being functions only of time, not of s. Okay, because remember that typically in most problems s is an unknown. We know it's a function of time, but we don't know exactly the expression for that function, how it is a function of time, and that's what is to be determined. And if you have, let's say, the acceleration as a function of both s and t, where s is an unknown function of t, then it becomes a little more complex to solve. Okay, right now this is quite straightforward to solve. Now, if you have this kind of an example, so this is what we are talking about over here, where we are looking at the various possibilities. We are looking at the definite integral, where we want to solve the speeds in terms of the magnitudes of acceleration. We are essentially integrating this particular equation. Okay, so when you are integrating this particular equation, we take the dv by dt, the dt to the other side. So we have this will imply v is equal to, sorry, dv is equal to a times dt, right? This is what we have, right? So whereas here the frame of reference was important, now we are dealing with scalar quantities. The frame of reference is not important, which is why I'm not saying with respect to which frame this derivative is taken. Okay, keep that in mind. So now coming to dv, it is a dt, and if I want to find the integration, I have to integrate both sides in the same manner. So if you're looking at, let's say, a definite integral, then you're integrating from let's say the initial velocity v naught to some particular instant of time where we want to get the velocity, which is v of t, right? Correspondingly here, what is varying is the time, so I have to specify the time, which could be, in this particular case, calling it 0. It could also be called as t naught if you want, and then you're going all the way up to a particular generic time t at which you want to determine this. So this is quite clear how this integrates to just v, and so since it's a definite integral, it just becomes v of t minus v naught, right? So which is what you see on the slide as well. And on the other hand, it remains, the right hand side remains as it is. You are unable to proceed further because you don't have a specific problem in which a of t is specified. Okay, this is a generic equation. Once a of t is specified, only then you'll be able to carry ahead this particular integration. The simplest case would be, what would be the simplest case of this? What function of a of t? Yeah, a of t is a constant. Even simpler than that would be that constant is 0, right? So if it is 0, then you just essentially have the Newton's first law kicking in. The particle's speed remains the same because there's no external force that is acting on it. So v of t is equal to v of 0, right? Once you have the case that you mentioned, which is a is a constant, so then let's just call it a without a constant. So then that becomes just an integral of a dt, where a is a constant, again going from 0 to t, right? So this is, so a can come out because it's a constant. So this just becomes a times t, right? Because the other limit is 0, so it doesn't contribute anything, right? So this v of t, we will generally just call it as v, knowing that it is a function of time, and we will call v naught usually as u. In many high school books you have this, and you have something probably you're familiar with, maybe you use different symbols, but this particular equation that a lot of high school physics students use quite frequently. But remember that this is under the simplicity that he pointed out, which is that a is a constant, right? Unless and until a is a constant, you cannot use this equation. So just be careful, just because you're familiar with this and many of the problems that you have for your homework, if you try to use this, you might end up with an error, because if you try to substitute a as a function of time over here, it's not going to give you the right answer. Okay, this equation is valid only when a is equal to a constant. And that constant, of course, could be either a 0 or a non-zero. For example, if there's a body which is just falling under gravity, then you're looking at g is a constant, that is the constant acceleration due to gravity, and a will take on the value of g depending upon the directions that you have for your coordinate system, it might be plus or minus g, right? Now that's what you have as one of the equations. Okay, same the other equation that we have, v is equal to dr by dt, or we can put it as v is equal to s dot. We can integrate that as well, okay, using the same process. So this, what this implies is that you have, you can take the dt to the other side. So you have v dt, and then you have s dot, which can be written as just the ds, because the dt is gone to the other side. And then you have from, let's say you're mentioning that as the whatever you're starting is s. So is s equal to s of 0 equal to 0, right? Without loss of generality, we can always have that instead of s naught, we can call it as 0. Doesn't matter. Just like we're calling the time there t naught also as t naught as 0, right? Now, so if this is what we have, so then you have integration up to s, and on this side you have an integration from 0 to t. Now you can substitute for what you already found out, v is equal to u plus at, on, because you didn't know the velocity, how it's a function of time, but the previous equations integration has given you how v is a function of time. So when you substitute for v using equation 1, the right hand side of course just becomes s, because you have the lower limit 0, so that's s minus 0, which is s, right? Now u is a constant, it's the defined initial speed that you have. A is a constant because all of this is valid only for constant acceleration, otherwise this is, so all of what I'm writing on the board right now is valid only when a is equal to constant. So therefore u and a being constants, I can very easily integrate the left hand side. So it just becomes, the first one becomes ut, and again the lower limit is 0, so that vanishes. So you have just ut over there, and then you have the second term is linear in t, so it becomes half t squared, 1/2 t squared, and that 1/2 t squared, again the lower limit is 0, so again it goes to 0. So you are ending up with this, which is what you got as s on the right hand side, which I'm shifting to the left hand side. Okay, this is your second equation. Okay, again something that is commonly used in high school physics in order to determine s if you know u, t and a, right? Whereas here, if you know the same u, t and a, you can determine v. So these are typically the two important quantities that we want to get to. What is the distance that is covered in a particular duration of time, and what is the speed that is reached after a particular duration of time. And both are functions of three quantities, namely the initial speed, the constant acceleration that is there, and the time you want to calculate it at, whatever the duration that is specified. Okay, so these are two equations. You might be familiar with another third equation, which is v squared equal to u squared plus 2as. Of course, you might have used different notations instead of v, a, u and s, but this is something that is very common as well, which is relating your final speed as a function of the initial speed, the acceleration and the distance. Any idea how you can get to the third equation? Because remember, I already utilized both my differential equations. I used v equal to s dot to integrate and get to this second equation. I integrated a equal to v dot to get to v equal to u plus at. I don't have a third differential equation. So how do I get to this third equation? There are multiple ways of getting to it. Anything that you can think of? How do I get to 3? Just think of what are all the variables that are involved over there. There is a u, there is a v. These are the two speeds that you have at time t equal to 0 and time arbitrary time t. Then you have the acceleration, which is causing that change from u to v. You have a distance which is covered during that period of time, which is s, and that period of time itself, which is time t. Okay, 1, 2, 3, 4, 5 variables that are involved. Okay, the question is, you're given any particular set, can you determine the other? So what we did here is to get s as a function of u, a, and t. So that's what the first equation did. It got you, given the initial speed, the acceleration, and the duration, we could get to the distance traversed. Okay. The second equation, what it did do, sorry, the other way around. So the first equation, what it did is to give you v as a function of the same three quantities u, a, and t. Because this is a typical way in which most problems are, simplest problems are posed. You know what is the starting speed. For example, when I'm dropping this, if I'm not pushing it down, I'm starting with a zero speed, right? It's starting with a zero speed. I know the acceleration, which is downwards, 9.8 meter per second squared. And I don't know the time it takes. So I might want to determine the time because I know the distance it's going to traverse, because I know the height from which this is dropping. Okay. So I can determine the time it took for it to drop by using this equation over here. It's a quadratic equation in t. One of the t's might come out to be negative, in which case that's not a valid answer, and therefore the positive is what you take, because you will have two solutions. So various problems can be posed in many different ways, where v and s are now known as functions of u, a, t, but you can of course manipulate those equations to get just like we in this example that we talked about, we are getting t as a function of s, u, and a, right? Now, so that's integrating one of these differential equations led to this, integrating this led to that, and of course we didn't use only the differential equations, we also used the initial condition where we were saying that at t equal to 0, s is equal to 0. So this was the initial condition at the lower limit of the integral that we already utilized. Similarly over here, we utilized this particular thing that at t equal to 0, the speed was v naught or u, right? So that is what we utilized in order to get to this equation. So always it's an initial value problem. It involves differential equations. It also involves initial conditions. You put together, you arrive at the solutions. So that's how we got to 1 and 2 using these two differential equations. So getting back to my question, how do you get the third equation? One of the ways that you can think of how you can get to the third equation.
Isolate t and then substitute the first equation.
Yeah, excellent. Yeah, excellent. So you already noticed that we have 5 variables over here, and notice which are the variables present in this. There is a v, there is a u, there is a, there is an s. So the only thing, as you mentioned, is to not have t, which means that I can use both these equations to eliminate t. Simplest way is to take this particular equation, v minus u divided by a is t. I can substitute for these t and t squared over here. Once I solve that, this is what I would get. Okay, that is one way which is very, very obvious and common that we can do. We can do something similar to what we did over here. Even though we don't have a third differential equation, we can create a third differential equation using these two. Okay, wherein we will not have t explicitly, we'll have only the s, v, a, and u, right? So u of course comes as an initial condition. We'll wait for that. But right now, if you're looking at this, let's say we will start with this particular equation, s dot equal to v. Which is nothing but ds by dt, right? Then you also have the other equation, which is a is equal to v dot, which is dv by dt. Now I want to eliminate t. So what I will do is I will divide and multiply this particular equation by ds. So it doesn't matter, the right hand, left hand side remains the same. Okay, so I can write this as dv by ds into ds by dt. Okay, immediately you recognize that s dot is nothing but v, this particular equation, right? So this is nothing but v, right? So now you have the right hand side can be written as v dv by ds, right? Now I can take the ds to the other side. I know a is a constant, so I can write ads is equal to vdv. Okay, I'm getting to where I want because this particular equation doesn't have t explicitly. Remember that you said that t is the only missing variable amongst the 5 that you have over here, and therefore you have this particular thing. Now I can, all that I need to do is just like what I've been doing on the top, to integrate both the left hand side and the right hand side from the time t equal to 0, which is at which point we know s is equal to 0, and it reaches some s of t at that time instant t, and a is a constant, so a can come out. The corresponding limits on this side is you start with a speed u and you end up with a speed v at some arbitrary time instant t, right? So when you do this, so this becomes, a comes out, so it just becomes as minus 0, so it's just as. Okay, on the right hand side we have vdv, so it becomes v squared by 2, 1/2 v squared, and therefore since both the limits are non-zero limits in general, we will have 1/2 of v squared minus u squared. Now you take the 2 to the other side, becomes 2as, which you see on the second term of the right hand side here, and then you bring the u squared to the other side, it becomes u squared plus 2as, and that's equal to your v squared. So this is also sometimes very useful when you're not interested about the time durations involved, but given the initial speed, acceleration, and the distance to be traversed, like in this case what happened, I can determine not only the duration it took, like using that particular formula, I can also determine at what speed this marker is dropping. At that point when it hits the ground, it is having a particular speed, and that speed can be determined by square root of u squared plus 2as. Okay. But again and again, I want to remind you that don't use these for generic problems, because this is valid only when a equal to constant. That constant can be 0 or non-zero, doesn't matter, but it is a constant throughout that duration during which you're considering. And to bring in Lalita's point over there, we can consider it in a piecewise way, right? There might be a particular kind of journey, let's say in the case of an aircraft, where, you know, like for example, when it's cruising, the aircraft is having a 0 acceleration, or it could have a particular constant acceleration also, during which you could probably use this for a rigid body dynamics problem. But remember that it's valid only during that portion of the entire flight, not for the entire flight where a will be varying as a function of time. Or it could be a piecewise function of time, and then you need to see which segments of that flight you could use it and which segments you cannot use it. Okay, so these are the simplest kind of thing that you have. And also remember that it's not only that a is equal to constant, but also that we are considering rectilinear motion. Okay, so in other words, we are considering everything is a straight line. So both these requirements are there, constant acceleration and rectilinear motion. Because if it's a curved path, you already see that the velocity direction is changing. If the velocity direction is changing, then the acceleration is there, right? And the acceleration could also in general be a function of time, and therefore you may not be able to apply even this particular second assumption that we invoked, which is a equal to constant over here. Okay, whereas what you have on the slide here are all generic things, even when a is a arbitrary function of time. As long as you know that a of t, you can carry out these integrations either by hand if you know the integration of that function, or numerically if you had just data points, accelerations at different instants of time you have noted down, and then let's say during a flight test or whatever, and then you can carry out these integrations. Okay, so that's the way we have been doing all of that is through actually specifying the limits of the integration over there. So that's similar to what we have here, just that you have a slightly more complication, that now a is not a constant, it's a function of time. Only given that explicitly what function of time it is, or given the a values as a tabulated for you at different instants of time, then you get a numerical integration done over from 0 to t in order to get this right hand side, and then therefore you can determine v of t as a function of v naught. Same thing, of course, the second step there, you have to integrate the second equation that we have. So both these cases, it's just these two equations that we are dealing with, okay, with a being a function of time, that is still valid, and then you have to integrate each of those equations using definite integrals. The alternate to that is, instead of applying the conditions, the initial conditions over there, you apply, you do the general integration with, and then you carry out that indefinite integral. You know how a is a function of time, and then you get a constant of integration. How do you solve for that constant of integration? You have the initial speed, okay. Remember, again, we are talking of rectilinear motion still. So in other words, the direction is not there. So we're not talking of an initial velocity, because that requires a vector which includes direction. Here we're only talking about the speeds, the magnitude that is involved. Similarly, the other equation that we have, that is your s dot equal to v, we are trying to integrate. Instead of s, I'm calling it r over here. So you're integrating that, because the position vector, remember, we are now talking about in a simplified form, which is by taking that to this particular point, and we are having this as the vector r from O to P, which is nothing but, its magnitude is nothing but s of t, right? So that's the s of t that you're talking about, or r of t. So once again, you'll need the initial position. So in this case, we just call that as s of 0. Without loss of generality, we can take that as 0. And whereas in a different problem, you could have perhaps called that r naught or s naught, which is what we have here, okay. So that gives you rise to another constant of integration, which can be solved by initial position. So initial speed and initial position come to the rescue for us to calculate C and C2. Then the same thing, these are all alternate ways of posing the same problem. Because you're studying the differential equations course in parallel, you will be able to appreciate some of these things. So here you have two kinds of initial value problems. I very briefly mentioned this in the previous slide. One is just having first order equations. In other words, the highest derivative that is there of the unknown is the first derivative, and the second one is the highest derivative is the second derivative. In this case, I'll have two variables to deal with, namely the distance traversed and the speed at any given point of time. Both those are the unknown quantities, v of t and r of t. And in terms of that, I have two equations, v dot equal to a, r dot equal to v, all of these being functions of time. And then I will be solving for v naught, and using the initial speed and the initial position, I'll be able to solve the entire problem. On the other hand, this is how many a times the problem might be posed. It's a second order differential equation now, a second order initial value problem, therefore involving two conditions because it's second order. One is the position at a given instant of time 0, t equal to 0. The other is the derivative of that position at that particular same time, and given r naught and v naught, I'll be able to solve this second order differential equation. So this will break for lunch, and we'll catch up again at 2 o'clock.